everybody again to another episode of the ideaXme show that profiles the humans behind the really big ideas that are shaping the world, inspiring the future and future creators. And for all those that like really great stories, I'm Ira Pastor, your health and longevity ambassador along for the journey today, but wearing a few additional hats because this is we're going into one major topic today. So time travel. Is the concept of movement between certain points in time analogous to movement between different points in space by an object or a person, typically with the use of a hypothetical device known as a time machine? Time travel is widely recognized concept in philosophy and fiction, and the idea of a time machine was first popularized back in the late 1800s by H.G. Wells in his novel The Time Machine. Forward time travel.
Well,
Of special relativity, general relativity, and the principle of making one body advance a few milliseconds compared to another body has been pretty well demonstrated in experiments comparing atomic clocks on Earth versus those in jets and satellites and so forth. As for the principle of time travel to the past, it is possible to find certain solutions in general relativity that allow for it in a theoretical system known as a closed Timelike curve, where the world line of a certain body, which is defined as the path that it normally traces in four-dimensional space-time, follows a rather curious path where it eventually returns to original locations in space and time as previously. In other words, closed time-like curves are mathematical results of physics equations that allow for potential time travel to the past. Our guest today, who I'm honored to have join us, who has been at the forefront of this theoretical area and who has been developing some rather novel theories on ways that light, specifically laser light, in essence can create closed time-like curves, is Dr. Ronald Mallett. Dr. Mallett is a professor emeritus in theoretical physics, Department of Physics at the University of Connecticut. With a bachelor's, master's, and PhD in physics from Penn State University, Dr. Mallett has lectured over the past few decades in areas as diverse as general relativity, gravitation, black holes, relativistic astrophysics, quantum cosmology, gauge theory, and time travel. He has published in numerous papers on black holes and cosmology in professional journals. His papers related to his time travel interests, also known as space-time twisting by light, include the weak gravitational field of electromagnetic radiation and a ring laser, gravitational Faraday effect produced by a ring laser, and the gravitational field of a circulating light beam. His breakthrough research on theoretical time travel has been featured extensively in media around the world, including NPR, History Channel, Science Channel, The Learning Channel, and he's the author of The Time Traveler, a scientist's personal mission to make time travel a reality. All that being said, Dr. Mallett, thank you so much for taking the time to come on the show today.
oh, thank you very much, Ira. It's a pleasure to be on.
It's a real honor having you. We typically start the show up by giving our guests the floor for a little bit just to talk about themselves. If you can really give the background to Dr. Ronald Mallett, where you grew up, how you developed this interest in all things Einstein, physics, time travel. Give us a little bit of the background story for those that haven't followed you for the last several years.
The thing is that my interest in time travel actually began with a personal tragedy in my life. I grew up in the Bronx in New York City, and I was the oldest of four children and a very happy family. My father was a television repairman who had served in the U.S. Army during the Second World War, was a battlefield medic, and he used the GI Bill to train himself to get education as an electronic technician. And he had a good job, and he was very, very well known actually in the type of work that he did. He actually had people like a lot of people probably don't remember the actor Walter Matthau, but my father repaired his television set, and he gave him an autographed picture of that. And I was very proud of him. I thought of him sort of the television repairman to the stars. And even though he worked hard, he had a lot of time for his family. He spent a lot of time with me. He would give me toys like a gyroscope, crystal radio set, and he would try to explain things to me. And the thing is, I idolized it. For me, the sun rose and set on me. To me, the day wasn't proper until I had a chance to walk home with him and carry his toolbox when he got off the subway in New York. Thing is he looked like he was very healthy. He looked robust. And that's why it was complete, utter shock when he died of a massive heart attack when he was only 33.
Mm.
And I was 10 years old at that time. And I was devastated. I mean, I was totally inconsolable. And I really didn't care whether I lived or died. I mean, the thing is that fortunately for me, among the gifts that he left me was a love of reading. And I loved reading science fiction. And about a year after he died, when I was about 11, I came across the book that actually changed my life. It was The Time Machine by H.G. Wells. And this book, it was a Classics Illustrated edition of it. And he, let's say that, I don't know, are we seeing images as well as my voice, or is it just simply a talking?
I see you fine.
Okay, the reason why I asked is I can show you the cover.
Absolutely. There it is.
There it is. This is actually the original magazine that started it all for me.
15 cents too.
Yeah, exactly. Not now, but then, you know. And the thing is that it said at the very beginning of it that scientific people know very well that time is just a kind of space, and we can move forward and backward in time just as we can in space. And I thought, wait a minute, it's saying that we can move backward in time as well as forward in time. And that was, for me, it was like a life preserver, because I thought, if I could build a time machine and go back into the past before he died, then I could talk to him again. I could spend time with him again. I could maybe tell him what was going to happen and save his life. So that became an obsession with me. And I have to admit, I have to say it was a private obsession. This was back in the 50s, before Star Trek. Mm-hmm. And people were not into science fiction as much as they are today. And I knew people that were worried about me, because I was very depressed after he died. And I thought I'd better keep this to myself. So I did. I didn't tell people that I wanted to build a time machine, but I did. My mother had kept the old parts, radio and television parts that my father had. And so what I tried to do was put that together with bicycle parts and everything. And I tried, and of course, when I turned the thing on, nothing happened. But I remembered that it said that scientific people know very well. So even though I was disappointed, I wasn't discouraged. I knew science was going to have to play some sort of role, but I didn't know what that was going to be. But as I said, luckily for me, I had this passion for reading. I mean, I was really a bookaholic. And after my father died, the family had been well-to-do before that. After he died, however, the family plunged into poverty. I mean, it was really difficult. I don't know how my mother did it, because she had 4 kids, you know, and the oldest being me at 10, and the youngest was actually only 4 years old at that time. But she did put it together. She had to get a job as a maid. It was a difficult time. As an African-American woman, it was even more difficult. Thing is though, that I would hang out at the Salvation Army bookstore, because you could get books there for about 5 cents. And I was using my lunch money that she would give us for school to buy books. And the thing is that which led to my getting sick, by the way, because I was getting thinner and thinner and thinner. But I came across the second book that changed my life. And that was extremely important. This was around the time I was about 12 or 13. Mm-hmm. And the picture on the cover of the book, it had a picture of Einstein standing next to an hourglass. Now, I knew that Einstein was this genius. I didn't know what it was he did, but I knew he was supposed to be this fantastic genius. And incidentally, it's an interesting coincidence that he died in the same year that my father died, in 1955. That's always been an interesting coincidence for me. But the thing is that since Einstein was standing next to an hourglass, I thought this might mean that Einstein has something to do with time. So I got the book, and even though I wasn't able to understand, you know, the details of it, it was a popular book, but I just didn't have the background. I did pick up the essence. It said that unlike Newton and Newton's theory, nothing can affect time. You can't alter time. Time is a river that flows and cannot be altered. according to Einstein, you can alter that river of time. You can actually change. You can actually, but I couldn't understand at that point exactly how to do it. But I knew that Einstein was going to be the key for me. And when I got out of high school, as I said, we were poor, so college wasn't in my future automatically. So what I did, in a sense, was follow my father's footsteps. I joined the Air Force. In my case, this was during the Vietnam War period, right after high school, and I eventually I became a computer technician. And I eventually, after I got out, I used the GI Bill in order to go to Penn State, and that's how I was able to get my bachelor's degree. And eventually, I was able to have a National Science Foundation traineeship that allowed me to get to do graduate work. So that was the way in which I paid for my education. Thing is that I decided to specialize in Einstein's area because I knew that this was going to be the key for me. I had to be careful though, because the thing is that time travel still wasn't an acceptable topic. But fortunately for me, there was an area of Einstein's work that overlapped, and that was black holes. And so by studying the theory of black holes, I realized that it would be possible to understand how time was being altered, but at the same time, it was a safe topic. And so that's where my major specialty was in the theory of black holes. And that turned out to be the case. And ultimately, after many decades, I really began to understand the different ways in which time could be altered according to Einstein's theory. And I then made my own breakthrough at the beginning of this century, interestingly enough. And so that's sort of the backstory. The real key is the fact that the real scientific possibility of time travel is anchored in Einstein's work. And as some of the remarks that you made earlier, he developed two theories. One was the special theory of relativity. Okay, the special theory of relativity was developed in 1905 by Einstein. And according to that theory, the time can be altered by speed. What he meant by that was that time for a moving clock slows down. The faster you move, the more time slows down. And he came up with that idea because he was studying what happens with the speed of light. And it turns out the speed of light cannot be altered no matter how fast or slow you're moving. But if the speed of light can't be altered, other speeds can be. If you're running next to a bicycle, the bicycle could be seeming like it's not moving next to you. But if you're standing still, the bike moves. With light can move, and there's nothing that you can do to change its speed. What Einstein realizes that means there's something strange happening. If light speed cannot be altered, something else has to be altered, and that's time. And according to him, time for a moving clock slows down. Now, the thing is that this has actually been shown. There is a device, it's called the Large Hadron Collider in CERN, Switzerland, which they have subatomic particles. These particles can only live for a very, very short time normally. And when they speed them up, they can get them to live 10 and 20 times longer than they normally would. And we've actually been able to see this even on a human scale, but not quite as dramatically. Also related to the remark you made, back in 1971, an experiment was done at the Naval Observatory in which they took two atomic clocks. One was put on an ordinary passenger jet. The other was kept at rest at the Naval Observatory. When they flew the passenger jet around the world and brought it back, they found that the clock that had been on the passenger jet had actually slowed down compared to the clock at its rest. Now, when I say a clock, I'm not just talking about a mechanical clock. Your heart is a clock. So this means that your heart rate would actually slow down. Your metabolism would slow down. You would not age the same way everyone else would. So even the effect was by just fractions of a second for the people on board the plane. But this actually meant they were fractions of a second younger than the people who were stationary. The thing is that once we have rockets that can go close to the speed of light, we'll be able to see this effect dramatically. We'll be able to person going close to the speed of light going out in space, for them, maybe a space trip might only take 5 years, but they could come back finding that decades have passed on the Earth. Interestingly enough, there was one science fiction movie that got it right that way. It was Planet of the Apes, the original one with Charlton Heston. You remember the astronauts went out in space, and when they came back, they thought they had landed on another planet that was dominated by apes. It wasn't the end of the movie that you find out that what had happened was is that the rocket they had been in had been traveling so fast that when it came back to the Earth, it actually was landing in the Earth's future, and decades had passed, and so they actually were back on the Earth and not on another planet. That principle behind what they were talking about was correct. The other part with the Planet of the Apes, that was another thing, but that part of it they had correct. The thing is, however, is that no matter how fast you go, this will lead you to go to the future, but you can't go to the past. Okay, it's not possible to exceed the speed of light. In fact, this very famous equation that people are familiar with, E equals mc squared, that's actually the law that prevents the possibility of traveling faster than the speed of light. Thing is, though, that it is possible to travel back in time, but it has to be done with Einstein's second theory. Now, I should mention his second theory. Einstein wasn't interested in the possibility of time travel, by the way. What Einstein was interested in is understanding the nature of light and understanding the nature of speed. But however, what he found was is that there was a problem when it came to gravity. And let me explain what that problem was, because this is the thing that led him to the second theory,
Sure.
which is the general theory of relativity. Okay, suppose that we think of the sun. Okay, imagine the sun, and in fact, I think I might have a little bit of a prop here.
Okay.
Okay, imagine that this is the sun,
Mm-hmm.
and imagine that this is the Earth.
Okay.
Okay, now we know that the gravitational force of the sun is what keeps the Earth in orbit around it. Okay,
Right.
the thing is that we also know that the Earth is about 93 million miles away from the sun. Okay, now what that means is that since the speed of light, which is 186,000 miles per second, okay, let's suppose that there was some sort of cosmic catastrophe that destroyed the sun. What will we see? And that's important, the way I say it there, because the thing is that it takes 8 minutes for the light to get from the sun to the Earth, which is interesting because that means that we never see the sun the way that it is now. We only see the sun the way that it was 8 minutes ago throughout our entire life. Now, if the sun is destroyed, according to Newton, what would happen is gravity would immediately shut down. So if gravity shuts down, there's nothing to keep the Earth in orbit anymore.
Mm-hmm.
But we would have this weird effect. Because of the fact that it takes 8 minutes for the light to get to us, if the sun were destroyed, we would be flying off into space, but we would still see the sun sitting out there in the sky.
Right.
So we would say, hey, that's a problem. I mean, that's a contradiction. Okay. So what Einstein said is that according to Newton, that implies that gravity can travel faster than the speed of light. So what he decided is that he would have to develop a whole new theory of gravity in order to prevent that possibility. That was actually the origin of the reason why he developed this general theory of relativity. Now, it took him 10 years to do that. Okay, he didn't finish it until 1915. The thing is the reason for that was the fact that he actually had to use a whole new mathematical technique called tensor calculus. And it took him that long to understand that technique and to use that technique in order to develop this new theory. It took him 10 years. I can explain to you in less than 10 minutes. Okay.
That's fine.
All right. The thing is that the way to do it, and this is an analogy, but it's a close analogy. Imagine that I had right now a rubber sheet in front of me. Think of a small trampoline.
Okay.
And imagine that rubber sheet represents empty space.
Mm-hmm.
And let's say that I put a bowling ball on that rubber sheet. What is it going to do? It's going to curve the sheet. Okay. And let's suppose I put a marble on the rubber sheet. The marble is going to roll down and hit the bowling ball. Right. Now, imagine that the rubber sheet is still there, but it's transparent. We can only see the bowling ball and the marble. We can no longer see the rubber sheet because it's transparent now.
Mm-hmm.
All right. So I let the marble go, and the marble moves towards the bowling ball. But since I can't see the rubber sheet, what I would say is, oh, somehow the bowling ball is pulling directly on the marble. But we know that's not what's happening. We know that what's happening is that the bowling ball is actually curving the rubber sheet, and the marble is moving along that to get to the bowling ball. In fact, what's interesting is that if I give the marble a little bit of a sideways motion, the marble to orbit the bowling ball due to the curved rubber sheet. What Einstein said is that's what's really happening in empty space. What's happening is the sun is actually curving the empty space around it. We can't see that curvature of space, but that's what the sun is actually doing. And what the Earth is doing is Earth is like that marble. The Earth is just moving along that curved space. And since when the solar system was created, the Earth had a little bit of a sideways motion. The Earth moving around the sun just like that marble due to the curvature of the space, like a skater on a roller derby ring. Okay, so what Einstein said is that gravity is not really a force at all. It is actually the curvature of space. So, and this is happening for anything. In other words, the Earth is actually curving the space around you. You can't see it, of course. When you jump up, you actually just fall along the curve of space due to the Earth. Okay, so that's his theory of gravity. His theory of gravity is what we call gravity. Is a massive object curves space. Okay. Now the thing is that this actually did solve the problem that he originally intended, because imagine that we go back to the bowling ball on the rubber sheet. Okay. What happens if I take the bowling ball off suddenly? If I take the bowling ball suddenly, the rubber sheet vibrates a little bit. Okay. What Einstein said is that what would happen if the Earth was destroyed? If the Earth was destroyed, that space would vibrate up and down. Okay. These ripples of space that vibrate up and down, when you calculate them, it takes 8 minutes for them to get from the sun to the Earth. Those vibrations of space are gravity waves. Okay. Because that's what gravity is. So what Einstein said is that if space is curved, when the sun is destroyed, it will take not only 8 minutes for light to get to us, but it would take 8 minutes for the effect of gravity being shut down to reach us. So if it's any kind of a consolation, we would still, not only would we still see the sun in the sky for 8 minutes, but we would still stay in orbit for 8 minutes until the effect. Consolation. But so that is actually his theory. Now, it turns out that in Einstein's theory, space and time are linked to each other. Whatever you do to space also happens to time. That's why it's called a space-time. Okay. And what Einstein said is that gravity affects time, okay, due to the fact that they're connected to each other. The bending of space leads to the bending of time. Now, what do I mean by the bending of time? According to Einstein, the bending of time shows up to us as gravity causing clocks to slow down. The stronger gravity is, the more a clock will slow down. In Newton's theory, nothing can change time. Speed can't change time. Gravity can't affect time, nothing. But according to Einstein, gravity, not only can speed affect time, but gravity can affect time. And that is the basis, that is part of his general, what's called the general theory of relativity. Now, you might say, has that been shown in a practical way? Not only has it been shown, but it's part of our everyday life. I don't know about you, but one of the devices that I have in my car that I use a lot when I'm going to a place that I haven't been before is the GPS. The way the GPS system works is right now, about 12,000 miles away from us, are 24 satellites that are orbiting the Earth. Any one of those satellites, there's 3 of them that are covering a certain patch of the Earth. These are what synchronous orbits. The way in which the system works is that your unit in your car has a clock in it. These satellites have a clock in them. And at a certain time, the satellite sends a signal which reaches the unit in your car at a certain time. Now, there's a very, very simple relationship between distance, speed, and time. Okay. If you know any two of those, you can calculate the other.
Mm-hmm.
So if you know the time the signal was sent and the time the signal was received, okay, and you know the speed of the signal, which in this case is the speed of light, you can compute distance. That's the way the GPS system works. However, it wasn't working. And when the engineers consulted with a physicist, they found out why. When they were setting up the system originally, they were assuming Newton's theory about how time is not affected by gravity. According to Newton, the time in your car, the unit in your car, was running at the same rate as the clocks on board the satellite because time isn't being affected. Okay. According to Einstein, since gravity affects time, your clock is actually running a little slower because it's close to the gravitational field of the Earth.
Mm-hmm.
It's running a little slower than the clocks on those satellite clocks are actually running faster than your car because they're farther away from gravity. So gravity has less of an effect. And it turns out that is noticeable enough because of the precision of that system that it actually throws things off because they actually have to use computers to calibrate the fact that the clock in your GPS unit is running slower than the clock on board the satellite, which is actually running faster. That is an effect that Einstein predicted. So I tell people that whenever they're using their GPS system, they should actually have a mental nod towards Einstein because without taking Einstein into account, we wouldn't be able to have the GPS system. So that is the real practical effect of gravity affecting time. But that is also a key to my research.
Okay.
Because in Newton's theory, okay, the only thing that can create gravity is matter. In other words, the gravity of the sun is what keeps the Earth in orbit. Okay, the gravity of the Earth is what keeps the moon in orbit. The gravity of the Earth keeps us, to the ground. But in Einstein's theory, not only does gravity create matter, light can create. Okay, I'm sorry. Not only does gravity, I should say, with the way in which I want to put it, not only does matter create gravity, but light can create gravity. And that's key, okay? Because the thing is that, remember that I said that, matter or gravity can affect time, okay? All right, so let's follow this. If gravity can affect time, and we know matter can create gravity, then matter can affect time. And we see that from the GPS system. But remember, since in Einstein's theory, light can create gravity, and this is where my breakthrough came in. If light can create gravity and gravity can affect time, that means light can affect time. That was the basis of my work because the type of light that I was looking at was laser light, but that means that laser light should be able to affect time. And in particular, the type of laser light that I was interested in was that could be created in a circulating path. There is actually a real device that's called a ring laser. And forget all the equation part there, but I don't know how clearly you can see the diagram there. It's a square.
You shifted over this way a little bit toward the end. Other way.
Oh, the other way. Oh, okay. Well, I'm trying to.
There we go.
Perfect. Can you see the square there?
Yep, there it is.
Okay. That square is a ring laser. A light beam comes through a semi-transparent mirror and then hits 3 reflecting mirrors and then goes around and around and around. That's what I mean when I say a circulating beam of light. Okay? All right. Now, that's important because it turns out that circulating beam of light, okay, remember what I said is that gravity is the curvature of space. Okay? So that means that gravity acts like a medium. So the thing is that if the circulating beam of light is creating this gravity, that means that it's going to actually cause space to become twisted. It will lead to a sort of a twisting gravitational field. Okay. The way to think about that is that imagine I had a cup of coffee here, and think of the coffee as being like empty space.
Mm-hmm.
And think of the spoon as being like the circulating light beam.
Mm-hmm.
And what happens when I stir the coffee? When I stir the coffee starts swirling around. Okay. That's what the light beam is doing to empty space. Empty space is like the coffee. Okay. And so as I'm stirring the coffee with the spoon, that's what's happening with the circulating light beam. The circulating light beam is like the spoon, and
Mm-hmm.
it starts swirling empty space around. And that's what I was able to find mathematically. As you mentioned, I'm a theoretical physicist. So the things I'm talking about, what I did was I was able to solve Einstein's equations, which is an interesting task. To solve Einstein's gravitational field equations to show that a circulating beam of laser light would cause a twisting of this empty space. Okay. Now you might say, how do you see it if it's empty space? Well, let's come back to the coffee. If I take a coffee bean, put it into the coffee, as I stir the coffee around, the coffee will drag the coffee bean around. Okay. Now the thing is that the thing that I would play the role of a coffee bean is a subatomic particle like a neutron. If I put a neutron into the empty space, okay, then when I turn on the laser beam, as the space is being twisted, the space would drag the neutron around. So even though I can't see the space being dragged around, I can see the effect of the space being dragged around because I would see the neutron all of a sudden starting to move, okay, in the space. But now it turns out so that's one prediction. That was the first prediction I was able to show. And in fact, that paper that I was showing you, that was that result.
Mm-hmm.
A circulating beam of light will cause a twist in the space. That could have applications itself because it could lead to a new type of propulsion in which you have circulating light actually moving space, and then objects in the space would be moved around. Okay.
Sure.
So that's one effect. The other effect, remember I said that space and time are connected to each other, and whatever you do to space happens to time. Well, that means that time is going to be linked to whatever is happening in space. And to illustrate that, let me grab a piece of paper here.
Mm-hmm.
All right. Now, on this piece of paper, I'm going to draw a timeline. Okay. And I'll show you the line in a minute.
Sure.
At the bottom of the line, I'm going to put yesterday, the past. At the middle of the line, I'm going to put today, the present. And at the top of the line, I'm going to put tomorrow, the future. Okay.
Mm-hmm.
Perfect. All of us, even though we're not aware of it, our entire life can be represented by a timeline, a straight timeline. Okay. Where the bottom of the line represents what we were doing yesterday. The middle of this line represents our talking today, and tomorrow is the future. Okay.
And just, I don't mean to interrupt, but is this what we refer to in physics as a world line?
That's exactly right.
Okay.
That's
sorry, I didn't mean to interrupt. But okay.
No, that's precisely correct. It's a word line, and that's just the way in which relativity would represent the way in which we travel through time. This world line is our timeline. Okay. Now, remember what I said, that space and time are linked to each other. If I'm twisting space and I twist space strongly enough, the second prediction that my equations show is that time will actually get twisted into a loop necessarily. Now look what this implies then. If I start at yesterday and I move along this world line to today, and
Yep.
I continue along the world line to tomorrow. But look what I can do. If I have twisted time into a loop, I can go from the future to where?
The past.
The past. That is what we mean by a closed time loop. That, in other words, what I was able to show mathematically was that as a result of solving Einstein's equations for a circulating beam of light, that it is possible to travel into the past. Okay, so that, and as I said, that's directly from Einstein's equations, but that was my, breakthrough, was being able to show that using circulating light, it was possible to do that. And that was published in a referee paper. I should mention that in physics, it's not enough just simply to say these things. Number one, you have to back them up with equations.
Sure.
And then you have to submit it to, a referee journal, and it's peer reviewed, and then it's published if they think that it's satisfactory enough. And it could be controversial, but nevertheless, as long as the mathematics is correct.
Look, I mean, anyone that takes the time to think these things through, as you have, and spend the time doing it, yeah, I mean, you clearly have put the time in to analyze these equations for a long period of time, and it's a very I'm very appreciative of the way you break down some of the most complex ideas possible for the lay mind. So I thank you very much for that, and I appreciate that background to it. I just as a side, and if this is a bad analogy, just say it's a stupid analogy, and we'll move on to something else. But you brought up Planet of the Apes before, with sort of the forward time travel thing. There was this movie a few years ago called Interstellar, with Matthew McConaughey and a bunch of other actors, and they were doing a lot of things the hard way, right? Going through black wormholes and dealing with all sorts of large cosmic stuff, and ending up, there's a scene at the end where, and it's one of the, it's one of those movies where I had to go online and I have to see what the hell the director's trying to do with this, and it involved fifth dimensional space and Kaluza-Klein equations and all sorts of stuff. That all being said, is there some relation? I'm just trying to put it in sort of a Hollywood type thought here. Is there some connection between what we saw in that model, let's say, and how we should envision a closed time-like curve in our four-dimensional or three-dimensional thinking? I don't know that equation makes sense.
The thing is that that's one of my favorite movies, by the way, Interstellar, because they got about, I would say, 80% correct about things. I mean, and that's as high, because normally it's usually like another movie that I enjoyed that just came out recently was Terminator, and they're usually about nearly zero. Right. So and which I still enjoyed the movie, but in Interstellar, and the reason why they got it really close to a lot of it correct was because one of the people who was a technical consultant was Kip Thorne, who just a couple of years ago won a Nobel Prize for the detection of gravity waves, which was another prediction by Einstein. In fact, I mentioned that the notion of gravity waves, and they were detected back in 2015, and he won the Nobel Prize for that in 2017. So he's an expert on Einstein's general theory of relativity, and he's contributed to the notion, in fact, of using wormholes as a possible vehicle for time travel. I should mention that there are other solutions of Einstein's equation. That one, the notion of using wormholes for time travel, is one of the results of Einstein's theory. We haven't seen wormholes yet, but theoretically, they're a possibility. So there's other techniques in there. Besides that, there's a man named Richard Gott at Princeton who's looked at the notion of what are called cosmic strings. That looked at the notion is that if there's a way of warping time. Now, let me point out the things in the movie that were accurate and the things that were speculative. The fifth dimensional stuff That was speculative.
Sure.
But the stuff that was right on accurate was the effect of black holes on time.
Mm-hmm.
That is real because, as I said, we already know that. We see that effect here on the Earth, that if you get close to a black hole, time will slow down dramatically.
Sure.
So when they were on a planet that was close to a black hole and time was altering at a very, very different rate for them
Mm-hmm.
than as it was for people that were away, that's spot on. And that is that if we were getting close to a black hole, we would definitely see the fact that a person that was near a black hole would be aging a lot slower than
Sure.
a person who wasn't. And so that effect that they had in the movie is correct and totally accurate. Okay. The representation of a black hole, as a matter of fact, another thing that has been able to be shown mathematically, but we haven't been able to get there yet to do it, is if you have a rotating, there's two different classes of black holes, although people don't know. If you have a non-rotating black hole, when you go to into what's called the event horizon is that region in which light completely gets taken back by the black hole. You know what a black hole is? Just simply a star that has used up its fuel and it begins to collapse. And as it's collapsing, the gravitational field around it becomes so great that the light that tries to get away from the star gets pulled back to the star. And that, of course, if you're out on the outside and all the light is being pulled back in, that's why you don't see it. It's called a black hole. And that area is called the event horizon, that area in which the light is pulled back in. Now, the thing is that if you go into a black hole that's not rotating, once you go in, that's it. Your history. There's no way of getting out. But it turns out, and this is real, that if the black hole is rotating, there are ways in which you can go in and actually come out of a rotating black hole. And when you do, this is actually accurate too. You can actually come out in the past. Okay. So the thing is that those aspects. So what they did was they mixed real physics with some speculative physics. That's why I said that they were about 80% accurate. Okay, because they really did put some real physics in what we really understand together with some speculative aspects of physics.
Yeah, so, I think I'd like to stay away from the black holes, and I was really trying to sort of make some mental analogies between sort of what happens when one encounters that, and then what we would encounter, or how we should think about a closed time-like curve generated by what I'll call a first generation Mallett device, or whatever the terminology is going to be. That being said, if we now time travel a little bit to the future and a fully functional prototype, what you sort of had planned for the next stage in developing I'll keep referring to this Mallett device. I don't know, whatever you want to, if you have
I like
what
that.
and for turning it on. And I know you talk about subatomic particles and obviously traveling to the past, very small amounts initially, but where is that body, we'll call it, going at this point in time? If it's sitting on your desk here, where are we sending it? Is the spatial component of it? In other words, if I want to send it to, I think you're in Storrs, Connecticut right now. Does that body stay in Storrs, Connecticut in a previous time period and that closed time-like curve, or just go walk us through that a little bit?
Now, I understand what you're getting at. Once again, let me give you a little demonstration.
Sure.
I don't have a time machine here. However, but the thing is that one of the things that isn't accurate in most time travel movies is the fact that, and this is where the Terminator really gets off. The thing is they have Schwarzenegger, the Terminator, coming back, and he just simply appears in the past. Okay, and one of the questions that people have asked is, well, if time travel to the past is possible, how come we're not inundated with time tourists, people from the future? The thing is that you have to remember that in real physics, you have to start at the point in which things were turned on. So, for example, in the work that I'm doing, if you turn the device on today, that's when it starts creating these time loops, okay? So if you put it on today and you leave it on, okay, and let's use this as an example. Suppose that I'm doing this in the laboratory and I turn the device on today. This is a slinky, okay? And the base of the slinky represents, let's say, where the Earth is right now today. And I turn the device on today. The device is not going to move. It's going to stay with the Earth. But the Earth is moving.
Okay.
So these time loops, as the Earth is moving, excuse me, the device is moving with the Earth. So the time loops are actually moving with the position of the Earth.
Okay.
So later the Earth is going to be over here, but the device is still going to be located in the same laboratory on the Earth from where it was in the future. In other words, it can be there. So, but look, what's happening is all of these time loops are linked together. So what I can do is I can travel along these time loops back. Let's say I turned the device on for 100 years. Then I can travel back 75, 50 years, all the way back to the time I turned the machine on. But I can't go earlier than that because it's the machine that's creating the effect. So what that really means is that with a real time machine, you can't go back earlier than when you turn the time machine on. So 100 years from now, someone could send back information or potentially go back anywhere in between, okay? But they can't go earlier than when the device is turned on. That's real physics, okay? And that answers the question about why we haven't seen time travelers from the future, because they have to have materialized in a machine that was turned on at a particular time. So what it says is that the first, human scale time machine just hasn't been invented, let alone a time machine in which you could send information back. That's a very, very important point. That's real physics. Now, the other part of that is the fact that and that's the reason why, as I said, most of the movies get that part wrong. There have been, I think, some films. I'm trying to remember but most of them, they don't get that part right, and they could do that. I mean, in other words, another movie that was really a fun movie to watch was Looper, and I don't know if I got that right. They could have done that by what they could have done was just simply said that in the past. A government project had developed the time machine, but it had been outlawed, and then crime, mafia types, got a hold of it and then used it for their purposes. So a lot of these movies could be altered in such a way that they could have, get the physics completely right about that. But that's the reason why we haven't been inundated with human scale time travelers. Now, that doesn't mean that we're locked out of the past totally, because let's suppose one of the things that we know now is that there are what are called extrasolar planets. These extrasolar planets, this wasn't known until the 90s. It had been conjectured, but it wasn't until the 90s that we actually knew that there were suns out there that actually had their own planets orbiting them. Up until that point, we knew there were other suns, but we didn't know that they had their own planetary systems. These other planets are called extrasolar because they're other suns. Okay. Now, since the 90s, we know that there are thousands of these just in our own solar system. What this means is that it's now being much more accepted in the scientific community that eventually we will find suns that will be somewhat like ours that have planets that are just at the right distance. In fact, they've even given a name for them because what most of these stars are either too big or the planets are too close, so it's too hot. Some of them, they're too far away, okay, so they're too cold. But there's a group, and you can guess from the name that they've given them, they're called Goldilocks.
Sure.
So they're just right, okay. And what we feel is that eventually there will be some that can support life. What this means now is now scientifically felt that the universe probably has a lot of life out there, that there are. Now, the difference between that and the UFO thing is that there's still skepticism, and I'm still one of those skeptics, that believe that we're not sure that that life has found us. Okay, that's where the UFO stuff. So now the community does believe, and I'm one of those. I do believe that the universe is teeming with life. I'm just skeptical about whether that life has gotten to us yet, because as a scientist, I actually have to see the proof of that. But there is proof, and we feel that very soon we will find planets that have that. Now, what this means is that some of these planets will be more primitive than us that have life, but some will be more advanced. And the ones that are more advanced, let's say that they have developed time travel, let's say 10,000 years ago. It will still have the same limitation. You would only be able to go back to the time the machine was turned on. But if we were able to get to those planets, then it would be possible to go back and to use their time travel to go back into our distant past. Okay. The whole problem there would be to find them and get to them in the first place. Sure. But so potentially, so it doesn't mean that forever we will be locked out. But as far as a terrestrial time machine is concerned, we're not going to be able to go back until we actually create the device itself. Now, the question that people ask me frequently is that two questions they ask was, when we do develop it, will we have paradoxes? You know, one of those paradoxes is the so-called famous grandfather paradox,
sure.
Which is illustrated in Back to the Future, where his mother becomes interested in him, you know, and so he begins to vanish. Okay, that's a paradox. Okay, the thing is that the other question is that when will this happen? When will we develop, you know, time travel? The other thing that people don't realize is just how expensive real science is. It's not going to be like the DeLorean or the way in which they show it in the movies, because remember I was mentioning about gravity waves that were discovered, and gravity waves were discovered as a result of two black holes colliding with each other. When two black holes collide with each other, they cause these ripples of space that we call gravity waves. Okay. Now, that doesn't sound like that should be too expensive. It turns out that the real experiment that was used to detect those cost $1.1 billion. Most people are stunned when they hear that, okay, because it doesn't sound, and that's real science. So the thing is that when people ask me, I tell them that real time travel is going to happen, or I should say real time travel, both to the future and to the past, will happen when we decide that we want to pay for it. It's just not something that's going to, you know, happen, and it's not going to happen tomorrow. That's the other problem. People are used to science fiction movies, and you know, they feel that this is going to happen in the next 2 hours, rather than the way in which it happens, which is usually over years or decades in real science. So, but as far as the paradox portion is concerned, there is another aspect of physics that resolves the notion of paradox. And everything that we've been talking about so far has been connected with relativity. Okay. The other main pillar, there's two pillars of modern physics. Relativity is one of them. The other is quantum physics. Now, quantum physics is a very, very weird thing. Unlike relativity, quantum physics does not allow exact predictions of the future of what's going to happen next. It only talks about the probability of events happening. Okay, in other words, according to quantum mechanics, you can't say, if I start off here knowing exactly where something starts here and the speed it starts here, I can't even know that exactly, let alone predict exactly where it's going to be in the future. But this is real because we know it's real, because we have personal computers, we have cell phones, all of these things work on quantum mechanics. In fact, our periodic table in chemistry that all of us have stared at in science classes from our childhood, those are all based on quantum mechanics. So we do know that quantum theory is real. The thing is that it leads to a weird prediction, though. There was a physicist, his name was Hugh Everett III, and this was in 1957. And as part of his PhD thesis, he developed a theory in which he decided not to just apply quantum mechanics to particular systems, but to apply quantum mechanics to the universe as a whole. Okay. And what he found was the following weird result, that for any event that happens, that event and its other possibilities also happen. Now, what he means by that is, let's suppose that uh, at dinner this evening, you decided to go to a restaurant and you were looking at the menu and you saw item A and item B on the menu. And let's suppose that you said, I think I'm going to have item B. At that very instant, according to Everett's, his world was called or his theory was called the many worlds interpretation of quantum mechanics, there would be a split of the universe. And when I say split, it would be a real split of it to suit two separate universes, not in our universe, but two separate universes. Sure. There would be a universe in which Ira has chosen item B on the menu, but there would be a separate, very real universe in which Ira has chosen item A. They would not know about each other. They would be in real separate universes that would be separate from each other. And this would be happening for everyone. This would be happening in what's known as a superspace, mathematically. All these universes would represent separate points in this superspace. And so this is almost like an uncountable number, because every single decision that you make or I make is going to lead to a split into a separate universe in which we've chosen that, and we've chosen the alternative in a separate universe. Now, the thing is that Everett was just interested in seeing if quantum mechanics, what it would lead to if you applied it to a universe as a whole. He wasn't interested in time travel. However, some decades later, in Oxford, there was a professor named David Deutsch. And what David Deutsch decided to do was to look at time travel from the standpoint of Everett's many worlds interpretation, which is now what we popularly call parallel universe. Mm-hmm. And what Everett found mathematically was that, not Everett, I'm sorry, what David Deutsch found mathematically was that when you apply Everett's theory, that it leads to the fact that when you travel back into the past, okay, you arrive in the past of a parallel universe. As soon as you get there. And in that parallel universe, you could do something like preventing your grandparents from meeting each other. Okay. You would just now find yourself locked into a universe that you were never born in. Okay. The thing is that, remember, I said there was a split. The other universe you don't arrive in. And that other universe leads to your grandparents meeting each other and having you. So that's how it's resolved. Now, so it says, according to Deutsch, time travel to the past is possible, but the past you arrive in is not the past that you came from. Now, that's just one of the possibilities. There's actually three possibilities. I've mentioned to you, there's the one in which you really do, the universe really does create a paradox. In other words, that you go back and prevent your grandparents from meeting each other. And when that happens, you disappear. Okay. That's it. That seems weird and contradictory, but perhaps that's the way the universe works. The way in which you could get rid of that paradox is this notion of parallel universes. Mm-hmm. The possibility which Hawking came up with is called chronology protection hypothesis. Okay. And what he by that, by the word, is the fact that the universe will act in such a way, and it's important to realize that a word I use, hypothesis, in there. This is not a proof. This is just Hawking's philosophical presumption. Is that what will happen is that the universe will actually always conspire to make certain that you can't affect the past. In other words, when you turn the machine on, it will break down, or something will happen to prevent you from going back into the past. But once again, that's not a proof. He just simply said that seems to be, to him, to be a likely possibility. Okay. So which one of these things will actually happen? We won't know until we actually do the real experiment, because that's the basis of physics. Okay. But the one thing that I do know, and I tell people, is that you have to be careful when people are talking about time travel and someone tells you, for example, I'm a time traveler from the future. Okay. What I tell people is, first thing to do is be polite with them. Okay. And then ask them, okay, well, where is your device? Because they could not have materialized into nothing. Right. And they usually find an excuse for telling you why they can't show you their device. Okay. I call it the Blue Dragon, but it's that what they'll say is, if some guy comes up to you and says, I have a blue dragon, a fire-breathing blue dragon at my home. And so you go there with him and say, yeah, okay. And he says, it's in my garage. Let me just go in and check. He comes out, oh, geez, he's sick,
Yeah.
So you're just not going to be able to do it. And so the next time, come back and he's just, he's sleeping,
Right.
But every time you try to find, to see this fire-breathing blue dragon, they will come up with an excuse. And that's what always happens. The government has shut down on it. So we can't, show it to you because it's so top secret that that you just can't get to it. Or I haven't gotten it working today, so I'm not going to be able to to show it to you. So the thing is that one has to be careful. And then the other thing is, as I said, is that one should be skeptical of any work that isn't based on Einstein's equations, because these things have been verifiable.
Sure.
Einstein's equals mc squared is real. I mean, we know that that's real.
I'm gonna go out on with this question here, and it's I know I'm speaking out of my domain, but bear with me for a moment, because you brought up a few things here, and number one, so this principle of not until we build first generation Mallett device and turn it on do we have the ability, in some way we're affecting the future in the context that now there exists one in the present that one potentially in the future could, in a sense, communicate with. I want to go into Einstein, and I know this is your specialty. I'm going to be talking out of my domain, but bear with me for 1 second here. I want to talk about this principle of retrocausality for a moment, because I know there are folks that, in the theoretical physics domain that talk about, that Einstein removed some things from E equals mc squared that he did not like because they had reverse solutions, let's say. I'm saying this the right way. That there were, in other words, that the concept of the future affecting the past in some manner he didn't like too much. I hope I'm phrasing this the right way.
Actually, that wasn't true, but that's okay.
Okay. All right. Well, that's great. Put me in the right place here. But there's just the general concept that, and I don't know if this more comes into play with quantum physics or whatever, but how the future in some manner could affect the past, just like the past affects the present.
Right.
How does that, in a sense, if we put a time machine aside for a minute and accept, okay, there's past, present, and future, that information in some form, doesn't have to be the time traveler himself or even something shot through the time machine, but just information from the future affecting the present.
Right.
And I know there's been some experiments done recently showing that in the quantum context that, hey, that this is maybe possible, that double slit experiment and all that. Walk us through that for a moment. And if I've moved too far out of where we should be, bring me back. But because this principle is kind of, when we talk about, you said it in the very beginning, and I'll shut up in a minute. The principle of a body, a clock, which is not necessarily this thing that's sitting on my desk telling me the time, but anything in terms of information that has some pattern being sent back as opposed to going forward. Walk us through that a little bit, if you would.
Yeah. Well, I mean, there really isn't a problem with it. I mean, the problem with it is actually, creating a device that would actually allow you to do it. But the future, you have to remember, the future isn't there already. Okay, that's an important thing. That really is an important thing. It's evolving. I mean, what we're doing now will change as we go along. And for one thing, and that's another thing in the special theory of relativity, when people talk about traveling to the future, you've got to realize that what they're doing is they actually, in Einstein's theory, there's always two observers. There isn't just one. In Newton's theory, there's only one. Okay. And what I mean by that, there's the person who's experiencing the effect, and then there's the person who's observing the person who's experiencing the effect. And what I mean by that is, for example, going back to the special theory of relativity, the person in a rocket that's traveling close to the speed of light, they're one observer. Then there's the person who's observing that person, okay? When the person observes that person, they see the person's heart rate slow down, their metabolism slow down. The person who's in the rocket, however, experiences nothing at all. For them, nothing strange is happening at all. That's important, okay? Because the thing is that they will age in their normal way as they're traveling to the future, okay? Now, since they've disconnected themselves, they literally now have disconnected themselves from everyone else's world line. So the Earth is going to go on the way in which it normally did. When the person who's on the rocket reconnects with the Earth, they will just find the Earth being however it had evolved between the time that they left and the time that they were in. They will have never been, they won't have influenced it at all. Neither will the people who are there influence that person. So the thing is that in a sense, they've disconnected themselves. The same thing happens if you're using a device either with, rotating black hole or my work. The thing is that once I'm going into the device and start going back in time, I'm no longer a part of everything that was happening. Everything that was happening in the past has happened.
Okay.
I would go back to an earlier point in which theoretically I might be able to see my earlier self. So I'm not encountering an identical me. I'm encountering a younger me when I go back to the past. Okay. Now, things will have happened in the in-between, and now I can influence them. So that's what I like to think of in terms of information, for example.
Sure.
And one question is what sort of information would you send back? Well, in the case of what we're talking of the device that I'm talking about, you could actually do. Remember, I was talking about using neutrons.
Yep.
Okay. The thing is that that computers work by using binary code. Okay, ones and zeros. Well, the thing is information could be sent back using neutrons rather. Neutrons spin like little tops. Okay, and they only have, and this is a quantum mechanical effect. A neutron only has two possible spin directions. It can spin up or it can spin down. That's it. Okay. And suppose that I assign a 1 to its spin up direction, and I assign a 0 to its spin down direction. Okay. And now let's suppose that I send a stream of neutrons through this device. Okay. And let's suppose that the stream is spin up, spin down, spin down. A computer connected to a neutron detector would see a 1, 0, 0. That's the number 4. So I can get information back to the past by using the spins of neutrons as a binary code. So that's one way one would send information back. When you get that information back, this is where a couple of possibilities exist. Remember, we were talking about parallel universe there. This is where we don't know until we do the experiment, what will happen. Let's suppose that the information that I am getting in my device, I have to decide whether that information is actually coming from my world or a parallel universe. Because if it's coming from a parallel universe, do I want to act on it? There's an uncertainty that's built into that retrocausality, because the thing is that if it's coming in from a parallel universe, I may not want to act on that information because it may actually contradict what I really need. And so if I act on it, it may actually lead to consequences that I didn't want because it's not actually coming from my universe. So one has to find a way of making sure of where that information is coming from.
Right.
But nevertheless, you can get the information, and it's possible, theoretically, to get that information. What you decide to do with it is another question, because you have that uncertainty that's built into it. But there is actually no problem other than the decision one makes regarding the information.
Fascinating. It's when I hear you talk about these things, it's beyond mind blowing, because it takes a special mind to to think through this. And as you were pointing out before when you were saying, time travel is an interest, but obviously one of those things, like I'm in the biotech space, and like in our world here, there's the things that people work on, and then there's the things that they dream about working on, but they don't talk about. Whether that's we work on correlates of consciousness or cognitive biology, but we don't want to talk about near-death experiences and things like that. But it's important that somebody thinks about these things, and the fact that in a world of studying gravity and astrophysics and quantum cosmology and everything else, that you spend time on this as well. You're creating the future. You're doing a very important thing in this process, and it's just I take my hat off to you. We've talked over the years, and it's just I'm really behind you 100%, and everything that you've been doing, and just the education and the knowledge that you're creating and giving to the world through this process is just it's invaluable.
Exactly.
And it's really been an honor having you on the show. And anything you want to leave off with in terms of some next steps? I know that you have some other scientists that you work with on these processes. Are you still in the process of raising money for the prototype? What's going on? What are your plans in the coming year?
Well, the thing is that one of the things that I want to emphasize to people is the fact that I have written this book,
Sure.
Time Traveler, and the thing is that I think it's important because there's a lot that we've discussed, but there's a lot that was left out because we didn't get a chance to talk about the other theories like wormholes and cosmic strings and other possibilities, and also the book goes into a little bit more detail about these things, also the Big Bang theory and also cosmology. There's a lot of other things that we haven't gone into, and also I think it's important to people to know what it's like as a scientist to try to understand things, and this is why I wrote this as an autobiography.
Sure.
One of the other things that I'm very proud about, besides the fact that the book's been translated into Chinese and Japanese and Korean, is the fact that Hollywood is now considering making a feature film of it.
Excellent.
And of course they're interested in it because of the autobiographical aspects of it, but it's something that I'm really quite proud of. And so the book is available on Amazon and can be ordered from any local bookstore. So, but that was something. So for me, it's letting people know the real possibilities that exist and have a real scientific basis, because I think it's important for people. And eventually, when we do master the possibility of time travel past, I think it's important for people to realize that is something that's going to eventually happen. And it's exciting to think about,
Sure.
what are the possibilities? What are the things that we'll be able to do with this? I want people to be informed. I also want them to be inspired as well. But my feeling also is the fact that, even though we have all of these possibilities, still, nevertheless, in the end, we only have the moment to live in. And that is what we have to do, is to make the most of that particular moment, as well as opening ourselves up to all the possibilities that are out there.
Absolutely.
And that's what I would like people to think about.
Absolutely. Absolutely. Well, it's been a real honor having you, Ron. For everybody that's been listening and that'll be watching on the YouTube channel, we've been spending time with the amazing Dr. Ron Mallett, Professor Emeritus, Theoretical Physics, University of Connecticut, a Master of Gravity, Black Holes, Relativistic Astrophysics, Quantum Cosmology, and Time Travel. Ron, thank you for taking the time to share your knowledge with us, sharing these ideas. And quoting from Einstein, I have actually in my yearbook from high school, I put his quote in about the most amazing thing in life that we can experience is the miraculous and the mysterious.
Yes.
And you clearly have the way that you not only look at the big picture stuff, but look through that window and are not afraid to deal with these big questions and think of these futuristic ideas that are going to become reality, as you say. They're going to happen. and you're making them happen. It's just a real honor, and that you knowing someone like you is out there doing these things. So Ron, really thank you so much for taking the time out of your schedule to talk with us and share your views. It's really amazing stuff.
Thank you very much, Ira, for having me on. I appreciate it.
Real pleasure.